In this video, we're going to explore the calculus of hyperbolic functions. We're going to apply the formulas for derivatives and integrals for hyperbolic functions. We're going to apply the formulas for the derivatives of the inverse hyperbolic functions and their associated integrals. We're going to describe the common applied conditions for a catenary curve. Now, the assumption is you have been exposed a little bit to hyperbolic sine and cosine. Well, hyperbolic sine and cosine is similar to cosine, sine, all of the regular trig functions. The regular trig functions are on the unit circle. However, the hyperbolic trig functions are on a hyperbola. So I would recommend, if you need a little refresher, or if this is the first time you have seen hyperbolic functions, that you consider watching some of the videos that are in the Canvas shell to explain a little bit about hyperbolic functions in general before you continue with this video. So I'd recommend you pausing it right now, go watch what a hyperbolic function is if you haven't ever seen one before, or if you just need to refresh. Now, if you remember them, or if you've never seen them before, this is how we define the hyperbolic sine and the hyperbolic cosine. Some will pronounce this as cosh and singe. I'm not a fan of that, so I will always say hyperbolic, which is a ton of things to say rather than the cosh and the sin. But I'm just not a fan of that. So the hyperbolic cosine of x is defined as e to the x minus e raised to the negative x over 2. And the hyperbolic cosine is similar in the way it's defined. The only difference is that this is a negative between the two terms and this is a positive between the two terms. Now the graphs on the xy plane of the hyperbolic sine, cosine, and tangent look like this. And you think, well, isn't that a parabolic shape? And then the actual answer is no, it is not a parabolic shape. It's not a parabola. It looks like one, but it's not. Just like this is really not a cubed, and this is really not a cube root, although they kind of are similar. We also have the hyperbolic cotangent, the secant, and the cosecant, all hyperbolic. And again, these look like graphs of stuff we've already learned, but not quite. Here's how we define it. Here is an alternate way to define it for hyperbolic sine, tangent, cotangent, cosecant, secant, and the cosine hyperbolic. Those are all hyperbolic, so with the h at the end. With the trig functions, we have certain identities. Well, we pick up some identities here as well, and these are similar to, but not exactly like the ones in the unit circle. Notice that to have this equal 1, I have to have the hyperbolic cosine squared minus a hyperbolic sine squared, not a plus here. In the unit circle, this would have been a plus. Notice how the hyperbolic cosine of 2x is not the same, but it's similar to what we would have seen in the unit circle. Same with the double angle for the hyperbolic sine, double angle for the hyperbolic tangent. The sum for hyperbolics for sine and cosine, and also for tangent. So these are similar, but they are not exactly the same. I will give these to you on the test if they're something that's going to be needed. We also pick up a whole bunch more. So we have the sum to product here. We have the sum to product for sine and cosine hyperbolic. We have the differences for the angles for hyperbolic sine and cosine, the differences for tangent. We also have the half angles. So we have a bunch of formulas that we pick up that are going to be similar but not exactly the same as what you would have seen these in our unit circle pre-calculus 2 class. Let's take a look at the derivative. So the derivative of the hyperbolic sine is the cosine hyperbolic, which is what we would have expected when we had seen the derivative of sine and cosine. There isn't really anything changed there. Notice how we define it. We do it with e raised to the x minus e raised to the negative x divided by 2, which gives us 1/2 e to the x plus e to the negative 2, or e raised to the negative x, which is how we define the hyperbolic cosine. So here are the table of derivatives for the hyperbolics. So here's the hyperbolic and here's their derivative. Here's the integration. Now remember, I will give these to you on the test. I don't give you these. But if you have the derivatives, because I gave you the derivative table, you should be able to go backwards and integrate them. So if I'm asked to find the derivative of the hyperbolic cosine, it is exactly what I would expect to happen. It's going to be the hyperbolic sign, but without the negative, and don't forget to do the chain rule. So this derivative is going to be, the derivative of a hyperbolic cosine is a hyperbolic sine of h, 3x plus 1, and then don't forget to take the derivative of the angle, which is just 3. So this is your dy dx, or y prime, if you will. Hyperbolic sine of the natural log of x, its derivative is going to be the hyperbolic cosine of that angle. It's kind of an angle. It's not really, it's kind of an angle. It's kind of not an angle. Multiplied by the derivative of the inner function, which is 1 over x. So the chain rule still holds true. Now, we take a look at the hyperbolic cosine squared minus the hyperbolic sine squared, and you think, wait, didn't we have a formula for that? And the answer is, yeah, we have a formula for that. So we come back up here and we say, oh, what was that again? Oh, this is equal to 1. So cosine hyperbolic squared minus sine hyperbolic squared is 1, which means its derivative is equal to 0. So this is your dy dx. So that is that one. So that's kind of nice. Now, when I have the natural log of the hyperbolic of secant tangent, its derivative is going to be 1 over, just like we normally have the derivative of the natural log, is 1 over the value I'm taking the natural log. So this will be the secant hyperbolic x plus the tangent hyperbolic x multiplied by, because I have to use the chain rule, the derivative of each value, the hyperbolic secant and the hyperbolic tangent, which will be the negative hyperbolic secant of x, hyperbolic tangent of x, that's the derivative of the hyperbolic secant. And the hyperbolic tangent is so plus the secant hyperbolic of x. Now you can see that I can factor out a secant, but it's not going to cancel with the denominator, so it is unlikely I'm going to take that extra step. Now I'm asked to find the antiderivative. So in other words, I'm asked to integrate. For me to end up with the cosine hyperbolic, that means I must have started out with the sine. So what I'm really doing is I'm integrating the hyperbolic cosine of 2x plus 1 dx. So if I let u equal 2x plus 1, du would equal to 2 dx. And you can see I'm missing that 2, so don't forget I have to make that adjustment. 1/2 du is equal to dx. So this is the integration of the hyperbolic cosine of u multiplied by 1/2 du. And to get the hyperbolic cosine, that must mean that I started out with the hyperbolic sine. Don't forget your plus c. And then don't forget to back substitute, which was the 2x plus 1 plus c. So this really isn't that bad. It's just that we're introducing another layer in the hyperbolics. And of course, I have the 3x squared. So again, what I'm asked to do is the integration. I'm going to do a little bit of u sub here. So I'm asked to integrate 3x to the third, the hyperbolic tangent of x to the fourth dx. So if I let u equal x to the fourth, du is going to equal 4x to the third dx. And you can see I'm missing the 4, so I'll have 1/4 du is equal to x cubed dx. Now, I don't have just the tangent. So because I don't have just the tangent as a derivative, then I'm going to rewrite this as, the integration of 3x cubed, and I have the hyperbolic tangent. I'm going to write that as a hyperbolic sine of x to the fourth divided by the hyperbolic cosine of x to the fourth dx, which means I'm going to actually change my u sub. So I'm going to say let u equal. Let u equal the hyperbolic cosine of x to the fourth. That means du is going to be 4x to the third hyperbolic sine of x to the fourth dx. And you can see I'm missing that 1/4, so I have 1/4 du is equal to x to the third, the hyperbolic sine of x to the fourth dx. So this, and that part right there, all gets replaced with 1/4 du, and this gets replaced with u. So what I really have is integration of 3 multiplied by 1 over u multiplied by 1 over 4 du, which is the integration of 3, I'm going to actually bring that out, 3/4, let me bring that out front, of 1 over u du, which is equal to 3/4 the natural log of the absolute value of u plus c, which is equal to 3/4 the natural log of the cosine hyperbolic x raised to the fourth plus c. All right, so let's take a look at my next one here, and it's going to be something similar. So I'm just going to let you do C. So go ahead and pause at this moment, and then I'm going to give you the answer. And hopefully when you did the integration, you have the natural log of the absolute value of 1 plus the hyperbolic cosine of x plus C as your final answer. Now this last problem is a little interesting. What I'm asked to do is to integrate the hyperbolic cosine of x plus the hyperbolic sine of x dx raised to the nth power. Now, if I rewrite this as the integration of the hyperbolic cosine of x plus the hyperbolic sine of x raised to the n minus 1 multiplied by the hyperbolic cosine of x plus the hyperbolic sine of x raised to the 1 dx, I haven't really changed anything. Now, because I haven't really changed anything, now I can do some u subs. So I'm going to let u equal the hyperbolic cosine of x plus a hyperbolic sine of x. Du is equal to the hyperbolic sine of x plus a hyperbolic cosine of x dx, which is still du is going to be equal to the hyperbolic cosine of x plus the hyperbolic sine of x, just by rewriting it. So you can see that this ends up becoming the u, du, so this is just nice du. And this is u raised to the n minus 1. So I really have u raised to the n minus 1 du. Now remember, when I do integration, I'm going to add 1 and then divide by that. Well, I'm dividing by n. And so this becomes u raised to the n divided by n plus c. But u just happens to be the hyperbolic cosine of x plus the hyperbolic sine of x raised to the n divided by n plus c. And that's my final answer. And it feels like magic, but it's not. It's actually really, really nice. So when we are looking at the calculus of the hyperbolic functions, we need to think about the inverses as well. If I take the graphs and I cut them in such a way in which my functions are 1 to 1, my sine hyperbolic inverse, its domain and range is everything. Because if you go up above and you look at the graphs of the hyperbolic sine, there's no problems there. The hyperbolic cosine does have to be cut at 0 for the original function, which means the outputs of the original function would be 1 to x, which makes that's the domain, and the other one become in the range. The hyperbolic tangent, it has a domain of negative infinity to infinity with a range of negative 1 to 1. Domains become ranges, ranges become domains. the hyperbolic cotangent, the same with secant and cosecant hyperbolics. And here are the graphs of the inverses. There's a lot of pages in that, but it is what it is. Now, alternately, just like alternately, we can describe the hyperbolic trig functions in terms of E. We can describe the arc, hyperbolic, sine, cosine, tangent, etc. in terms of the natural log. And sometimes that is way more beneficial to write it in this form versus this form, especially if I have to do integrations or derivatives. So if we use implicit differentiation, and so if I am trying to find the sine hyperbolic, the hyperbolic sine of y is equal to x, because I started out with y is equal to the sine inverse of x, taking the sine hyperbolic of both sides and solving. And here is what the derivative of the inverse would look like. So once again, I give you these derivatives for the test. I don't give you the integrations. Notice how similar these are. These are like, wow, this reminds me so much of my trig inverse derivatives. They are similar, but they're not the same, and it's really easy to get mixed up. So on the test, if I give you something that looks like this, make sure you're not using the regular unit circle trig function. You're actually using the hyperbolic trig function. So when we're asked to find the antiderivatives of the tangent inverse, find the derivatives of the tangent inverse. This is a nice straightforward. I'm going to use this one for the first one. And then don't forget, I prefer to use u. So then this is u squared multiplied by u prime. So this derivative is going to be 1 over 1 minus 4x raised to the 2 multiplied by the derivative of 4x, which is just 4. And then with the hyperbolic sine derivative of the hyperbolic cosine, I end up with 1 over the square root of 1 plus the hyperbolic cosine of x, the quantity squared, times the derivative, because I'm using the chain rule, of the hyperbolic cosine, which is the sine hyperbolic of x. So hopefully you're not seeing that these are all that bad. They could be a ton worse. So then I have e raised to the hyperbolic sine inverse of x. So this derivative is going to be e raised to the hyperbolic sine inverse of x multiplied by the derivative, which is 1 over the square root of 1 plus x squared, and then derivative of x, which is just 1. This derivative is 1 over the tangent inverse hyperbolic of x multiplied by the derivative of the tangent, which is 1 over 1 minus x, the quantity squared, divided or multiplied by x prime, which is just 1. All right, so now what we're going to do is find the antiderivatives. Now remember, all I have is the derivatives. So I'm going to look to see if I can find one that looks like my derivatives. And if I take a look at a, I have dx over a squared minus x squared. And you know, since I don't give you the table of integrations, but I do give you the table of derivatives, let's rewrite this as dx over, I'm going to factor out an a squared, so I have this 1 minus x over a, the quantity squared. And so by factoring out that a squared, I'm going to have 1 over a squared, the integration of dx over 1 minus x over a. This is squared. And so we know that this is the tangent inverse, and it's also the cotangent hyperbolic. So you're like, well, how do I know which one to use? So this is either the hyperbolic tangent inverse. Oh, don't forget the 1 over a squared. 1 over a squared. The hyperbolic tangent inverse of x over a plus c. Or this is 1 over a squared, the hyperbolic cotangent. So cotangent hyperbolic inverse of x over a plus c. And you're like, How do I know which one to use? Well, you would use this one if the absolute value of x over a is less than 1, and you would use this one if the absolute value of x over a is greater than 1. And if you're not sure, because you don't know what a is, I would recommend on the test you write down both of them. However, I will give you a better idea so you know which ones to use. Let's take a look at b. With b, I have x dx over x squared plus 1, and I'm like, man, I really want to use one of our hyperbolics. In this case, I'm not going to. This is a nice u sub. So just like I talked about in class, I said, just because the problem lands in this section does not mean that you have to use that knowledge from that section. It may be asking for knowledge that you've done before. If you let u equal the x squared plus 1, and du is going to give you 2x dx, which is almost the numerator if you divided both sides by 1/2. So this really is going to get replaced with 1/2 du, and this is going to get replaced with u raised to the 1/2. So this integration becomes 1/2 u raised to the negative 1/2 du. So it really wasn't actually a hyperbolic. And that happens. This one's actually missing the dx, so make sure you write that dx on your notes. I don't know what happened there. Okay, now let's take a look at c. I'm not going to finish b for you because you all know how to do u sub at this point. So if I take a look at b, I have x on the outside, and I have 1 minus x squared. Now, if I rewrite c as a negative of 1 over x, the square root of 1 minus x squared dx, then this becomes the negative secant, so it's a negative secant hyperbolic inverse of the absolute value of x plus c. So in other words, this is just the hyperbolic secant inverse of the absolute value of x plus c. So that's really nice. And as I take a look at d, now d, you think, man, could I do u sub? Well, no. And the reason you can't do u sub is because if you let u equal that denominator, e to the 2x minus 1, and du would need 2e to the 2x. And notice how this is just x. Because that's just x, then this really is a hyperbolic. So let me erase that. Let's let u equal e to the x. And then du is equal to e to the x dx. So then this gets replaced with du, and this gets replaced with u squared. So then this becomes integration of 1 over the square root of u squared minus 1 du. Now I look at my derivatives, and I look for the one that has a derivative that matches that, and that one happens to be the cosine hyperbolic inverse. So this is the cosine hyperbolic inverse of u plus c. Now I back substitute, so I have the cosine hyperbolic of e to the x plus c, and that's my final answer. Now on e here, it's going to be something similar. I forgot the dx because I really didn't think it was important. So I'm going to let u equal x squared, and du is equal to 2x dx. So then this gets replaced with du. This gets replaced with u squared. So this becomes the negative integration of 1 over u squared minus 1 du. So I look for the derivative that matches that, and there isn't one. However, if I pull that negative back in and put it on the denominator, I'm going to have the integration of 1 over 1 minus u squared du. Oh, that's a hyperbolic tangent, depending on what u is. So this is either equal to the hyperbolic tangent inverse of the absolute value, or not even u, not absolute value, so of u plus c if the absolute value of u is less than 1, and the hyperbolic, and don't forget the h, the hyperbolic cotangent of u plus c if u is less than, or excuse me, greater than 1. And then, of course, we actually need to put in the x squared. So I need to go back and put my x squareds in the right places, do my back substitution. X squared, x squared, x squared, x squared. Okay. Here is a couple of examples. We have a chain that hangs from two posts 2 meters apart to form a catenary, described as the equation y is equal to hyperbolic cosine of x over 2 minus 1. Find the slope of the catenary at the left fence post. So in other words, what I'm asked to do is find the derivative, and then evaluate it when x is equal to 2. So what I'm really want for, because I see the slope, that should say, oh, derivative. So I want dy dx. This is going to give me 2. The sine, hyperbolic sine of x over 2, and then minus 1 will go to 0. So, and then the derivative of x over 2, which is 1/2. So this gives me the sine hyperbolic of x over 2. Now, since I have the 2 meters, I'm looking at 2 meters apart. So if I want to draw a quick little picture, 2 meters apart, I'm going to make an assumption that it's going to touch the x-axis at 0. That means from here to here is 1 meter, because the entire distance from post to post is 2 meters. And so I get to choose where I put my x and y axis. And so I'm going to put that as being the input when x is equal to 1. Because I want the left post, I'm going to have x is equal to -1. So in other words, I want dy and dx evaluated when x is equal to -1. So this is equal to the hyperbolic sine of -1/2. Now, you're like, how am I supposed to figure out how to put this in a calculator? Well, if you don't have a calculator, we can go back to the way that we define the hyperbolic sine, and then just put that in that place. Now, and what I mean by that is how I defined it in terms of e. So we know that the hyperbolic sine of h of x is equal to e to the x minus e to the -x divided by 2. So then this must be equal to e raised to the -1/2 minus e raised to the -1/2 divided by 2. And whatever that is the actual answer. Telephone line is a catenary described by y is equal to the arc hyperbolic cosine of x over a. Find the ratio of the area under the catenary to its arc length. Well, we haven't learned arc length at this point, so if this is on your homework, just let me know and I'll remove that and put it in the right place, because we haven't learned arc length. We're not actually following the textbook in order, because I want to get all of the integrations and derivatives underneath our belt before we go to the applications. So we will come back to this question when we get to 2.4. So right now, if this shows up on your homework, let me know and I'll just move it into the 2.4 homework. And that's it for this video, so we'll see you in class.